morning, students. In the previous class, we learned about the basics of the sampling theorem. We just know about the importance of the sampling in the communication system, that conversion of that continuous time signal into discrete signal. What was the sampling theorem? The sampling theorem says that any signal can be reconstructed back from its original signal if the sampling frequency is greater than or equal to the twice of the message frequency. So we have done all the mathematics and conclude that. Now in today's class we will discuss about the sampling techniques. How many sampling techniques are there? There are basically three types of the sampling techniques. One is impulse sampling, natural sampling, and last one is flat top sampling. The impulse sampling is also known as the instantaneous sampling or ideal sampling techniques. These are the ideal technique. The impulse sampling is the ideal technique. So what it uses, the impulse sampling basically uses the principle of simple multiplication. It can be performed by multiplying the input signal with the impulse string. So you have a one signal xp, you have to multiply this signal with the impulse string. So we know that the function impulse function is only valid for delta 0 equals to 1, otherwise it's 0. So impulse train means this delta is valid for a particular time interval, ts, 2ts, 3ts. So train is given by the this function is given by the function is just distributed along the n is equal to minus infinite, n is a value, minus infinite to plus infinite, function of delta t, valid for the t minus n ts, and ts is the interval. Okay, t is the period and t is the interval. So simply we get the output signal. Output signal is just having the shape of the this input signal. Okay, or equally distributed impulses, that's t, ts, and 2ts. To construct this kind of signal, we need a circuit that is known as sampler circuit. In sampler circuit, you have a one input xt, one switch which having frequency 1 upon fs, or we can say that the period switching period is 1 upon switching period is equal to 1 upon period. Your output. So what is the output is given by a simple input is multiplied by impulse train. Impulse train, okay, xt multiplied by impulse train. The function of the impulse train is given by x is equal to n is equal to minus infinite to infinite delta t minus nts, as we seen earlier. So after solving this, simply y delta t is equal to summation of n is equal to minus infinite to infinite. When xt came multiplied by this function, x is uniformly distributed along this t-axis. So it is given by the x n of t delta t minus nt. We can see here that this xt is uniformly distributed to the minus infinite to the plus infinite at a sample value of ts. Okay, so we will get this output yt in time domain. Okay, this is in time domain. In time domain we are getting the output like this. So to get the spectrum of the sample signal, consider the Fourier transform of the equation. When we do the Fourier transform, as we know that this delta function, after solving this delta function, taking the Fourier transform, we are getting 1 upon t, because amplitude is 1, we are in unity magnitude. If amplitude is a, then it's coming out to be a by t. Okay, pulse width is 0. In this, the pulse width is 0, so equals to 0. Pulse width is 0. This is the ideal pulse width is 0. That's why we get the output 1 upon t. If you want to solve it also, then you are after solving using the Fourier series expansion and Fourier transform, you will get the output S. So this is called, because the pulse width cannot be zero and generation of the impulse train is not possible practically. What does it mean? It means this pulse width cannot be possible. Okay. So the signal energy is very low. Okay. So these are the two basic disadvantages associated with the impulse sampling, that is, it is not practical and it has high noise. What is the output spectrum? This is your input time. And so on. If you want to reconstruct the signal, just pass through a low pass filter. After passing a low pass filter, you will get low pass filter or band pass filter. You will get this kind of energy. Okay. Next kind of sampling is natural sampling, which is more practical than the impulse sampling. Natural sampling is very similar to the impulse sampling, except the impulse train is replaced by pulse train. Pulse train. What is pulse train? In this time we have a certain width. There is a certain width. The pulse. Okay. Impulse train is replaced by a pulse train. Input is same, but instead of using impulse, in this case we are using a square wave pulse train. Okay. The output is taking the shape of the input. Okay, like this. Please consider this. Please note this. The top of this square wave is taking the shape of the input waveform. Okay, this is natural sampling. Naturally, the top is naturally taking the shape of the input waveform. For this purpose, we need a similar circuit. In this similar circuit, we have this square wave given to the switch S. Okay, so the output waveform is again given by the xt is multiplied by pulse train. Pulse train is given by, let us say, pt. This pt, this function is pt. So xt multiplied by pt. Here by pt. Pt is given by the summation is a pulse train minus infinite to infinite. P of, in previous case, that was delta. Okay, because it was impulse. This time it's a pulse. That is why we are denoting as a p. Pulse train p, t minus anti. This is equation 1. So in previous case we have considered that the magnitude is 1. For example, in this case, if magnitude is a, pulse width is tau. In previous case, impulse size is tau is equals to 0, and the time period is 1 upon fs. Okay, so to solve this, we need to represent n s dt. This is simple formula to get the Fourier transform. And after solving this, you are getting 1 upon t p and omega s. In the previous case, just remember, in the previous case, the case of the impulse function, when you solve all this, you are getting 1 over t. Okay, here again I am taking the magnitude a is equal to 1. So I am getting this 1 over t p n of omega s. In previous case, just go through the previous slides. And this this only one, delta is equal to 0 is equal to 1. Okay, in this case, after solving this, we are getting 1 upon 2 along with omega s. Okay, so just substitute outside outside the equation, that is with this. So substitute the value of the pt in equation 1. Equation 1 was xt into pt. Xt is 1 over t summation of minus infinite to infinite p and omega s e to power p and omega s. Then you are getting this. This function is again xt is in this equation. So it's time domain. Then this pulse width. So if you want to get the spectrum in frequency domain, convert this signal into frequency domain, then take the Fourier transform of the both side. Taking the Fourier transform of the both side, you are getting n omega s and Fourier transform xt e to the power n omega. So this is the basic formula. It can be written as x omega minus n omega s, which is very similar to the previous case, but only difference is that is pulse function. So the we know that after all, if we go through this Fourier series expansion in Fourier transform, then we know that the Fourier transform of any square wave is a sinc function. Sinc function, I hope you understand that sinc function. Sinc function is a dying out function. Its value is maximum at the center, and then it bounces to less values. So your spectrum in this, the input spectrum is same as minus fm to fm, that is the bandwidth, and your output spectrum is dying out. It's a sinc function. Okay, it's a sinc function, so it's a dying out function. Okay, you want to take the uh, spectrum, you want to recover the input from this spectrum, then you need to pass through the filter and just extract the center frequency, this fm message frequency. Last one is flat top sampling. What is flat top sampling? Flat top sampling is very similar to the natural sampling, but instead of naturally in the natural sampling, the output is naturally follows the input waveform. The flat top sampling, the output waveform is rounding off. We will round off the output top. Okay, and for this purpose, we use this switches circuit. XT, G1, G2 are two switches. One is sampling switch, one is discharge switch, and capacitor is needed. Okay, so during the transmission, if noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in the form of the flat top. Here, the top of the samples are flat. That is the major difference. The top of the samples are flat. In the previous case, you can see that the top is not flat. Okay? Top is taking the shape of the this input waveform. The flat top sampling, the top is completely flat. Okay, this is the basic circuit. So again, theoretically, the sample signal can be obtained by convolution of the rectangular pulse with the uh, for how we get this flat top sample. Simple is take a square wave, simply multiply with this impulse output, simple impulse signal. You are getting a flat top signal. This is the basic approach, that yt is equal to pt multiplied by y of delta t. Delta t, y of delta t, impulse signal. Okay, in the first case we have learned this impulse signal. Just multiply square wave to the impulse impulse signal. So to get the sampled output, consider the Fourier transform taking the both side. Y of omega is equal to Fourier transform of this p of t by the y of omega. After solving this, we are get the this set of sample. One last approach, one last thing is Nyquist rate. What is the Nyquist rate? Nyquist rate is the minimum sampling rate at which the signal can be converted into sample and recovered back without the distortion. Very similar to the this sampling theorem. Okay, so Nyquist rate Fn is given by the twice of Fm. Fn Nyquist rate is given by twice of Fm hertz. Nyquist interval is 1 upon f of n. Okay, for example, just this case in previous class, this perfect sampling. This fs is equal to twice of n. This is Nyquist interval. Okay, to get the perfect sample input. Okay, in today class we learned about the types of the sampling technique: impulse sampling, natural sampling, and factor of sampling. Impulse sampling is practically impossible. Natural sampling, the output waveform simply follows the input. Okay, factor of sampling, the output waveform, the top is being flatted out. Okay, so simple mathematics are there, and we know that the natural sampling and the factor of sampling, the output is sink function, it's a dying out function. Okay, so you will get a spectrum like like this. You will get a spectrum like this, dying out spectrum. Okay, you need to recover the original signal, then you have to pass through the filter process. Finally, the Nyquist interval for perfect sampling, which Fn is equal to given by the price of Fn. Nyquist rate is Fn is equal to twice of Fn, and Nyquist interval is given by 1 upon Nyquist rate. Okay guys, thank you so much for